Welcome to our lecture on compiler construction. In today's lecture we are going to have a look at our first data flow analysis. So today we're going to take a look at live variable analysis. So live variable analysis is an important analysis to enable optimizations, and live variable analysis is a backward analysis. So we're beginning our analysis at the end of our program or our part of the program we're considering, and then we're going backward throughout our control flow graph to analyze the live variable values. So in other terms, for each variable x in the program, we try to determine where is the last program point p at which this specific value of x is actually used. Or to give a bit more detail on this, if we have a variable x and a program point p, we are trying to determine if the value of that variable x at this program point p can still be used along some path that is starting at this program point p. So if this is the case, so we are at a program point p, we have a variable x, and this can be used after program point p, we say variable x is live at program point p, and if this is not the case, our variable x is dead at program point p. So obviously our programs are not simple linear executions of instructions, but we have branches, we have loops in our program, so live variable analysis must take control flow into account. So obviously we need to solve a data flow problem here. So let's look at an example. So we have a program point p here, and at this program point p0 we have an assignment using a variable x in the preceding basic block, and we say at this program point p0 our variable x is live if there is a path to another block, say p1 down here, where the value at p0, so the value of x at p0, is actually used. So of course programs can branch. So if we have a situation like this, so we have a certain point in our program where we can branch to the left here to p1, p2, and to the right to p1 here, we can have different behaviors of our program here. So we see we have a program point px here, and if we go to the left at p2, the value of x is overwritten with some new assignment here. So beyond px on the path towards p2, our value of x is no longer needed, so our value of x is dead here. And so for live variable analysis, we have to observe for each variable and for each program point where is the last program point beyond which the value is not used here. And then we have to trace back from the uses to the definitions of variables. And then we need to observe the first definition in backward direction that actually reaches that use. And this first definition that reaches that use kills all uses backwards of it, so further up in our control flow graph. So a variable is live at a program point p if its value is used along at least one of the passes that emerge from point p. So a use of variable x prior to any definition in a basic block means that x must be alive, and definition of x in a block b prior to any subsequent use means that all previous uses must be dead. So essentially we have a basic block here, we have some outsets which in turn will be the insets of the subsequent basic blocks here, and our analysis runs backward, so against the direction of our control flow graph, to actually figure out the liveness. And from this we can obtain the sets we are interested in. So we are interested in our gen set. So this is a set of variables that is used in a basic block B. So this represents the upward exposed reads of variables in block B. And we're interested in our kill set. This is the set of variables we are defining in B. And so we can say our set out B is our join of all the in information of the succeeding blocks. So we're going back here and join this together. And our in set is the set used in block B joined with the out of block B, and from this we subtract the variables we define in block B. So to implement live variables analysis, we start by initializing in B to the empty set, and then using the formulas we've just seen on the previous slide, we compute genUse and killDef for each basic block. So we're tracing backwards from the end of the block to the beginning of the block. We initialize the last instructions out set to the empty set, and then we apply the formula we've just seen. So we set the in set to the use set joined with the out set minus the ones we've defined in this instruction. So when we did this for each instruction, we can actually iteratively apply these relations to the complete basic block until we hit convergence. So then we have out B is the join over all successors of B of their in values. So let's look at a detail here and an example. So we want to compute use and def for a given basic block. So first we start with the use, and we have these three instructions here. So t equals a plus 1, b equals t, and then a branch ending our basic block. So if a equals b, we jump to a label L2. And we have our formula here again, just to give it again to be able to construct our sets. So in I for each instruction is the set of variables used in this instruction joined with the out variables minus the defined variables for each instruction. So now we're starting from the end of our basic block here. So with the last instruction, which is our if instruction, and we've set our defs here are 0, so we just have an if, so we don't define any variable here. And of course, for this instruction, we are using two variables here. We're comparing a and b, so we're using a and b. For the instruction on top of that, b equals t, we are using t, we're reading its value, and we're redefining b because we're assigning something to it here. And our first instruction on top uses variable a and defines variable t. So now for our analysis of the whole basic block, we start at the end of the basic block and we set our set out is the empty set, and accordingly our set in, we construct it according to our formula, is the use joined with out minus def. And so now we can replace use and def in this formula here. We have out. So we get in equals our use, AB, joined with that simple out is the empty set here, def is the empty set here. So AB joined with the empty set, of course, remains the set of A and B. So now we can go backwards through the instructions in our basic block to look at the next instruction before the if. So we know out was AB, so giving the out and the information we obtained about this instruction here, use and def, we can again apply our formula here and replace the variables here by our concrete values we've determined already. So we say in is equal to our use, which is t here, joined with our out variables, which is AB, and from this we subtract our def variables, which is b. So AB minus b is variable A and t together is a set of variables A and t. And now we can do this one more time. So we know the outset for the first instruction is A and t, and we can again, using the values for the instruction we've determined already, determine the inset here. And so we obtain in is again the use variables in the block A joined with the out variables AT we've determined in the previous step, and from this we subtract our def variables t, so AT minus t is A joined with A, well, leaves us with a use of A for the whole basic block here. Now we have determined the use set of our basic block here. So in the next step, we are trying to determine the def set for our basic block here. So we have this formula here. So in def for our instruction is the defined variables in the instructions joined with the out def. And again, we start with an empty set out def here, and we go backwards through our instructions of the basic block. And so our out def was empty. We didn't define any variables in this if instruction here. So empty set joined with the empty set, of course, remains the empty set. So we have a new out def, which is still the empty set for the second instruction here. So now we join this with the defs here. Def is B, joined with an empty set remains B. This again turns into the out def for our first instruction. So out def is B, and we have another def defined variable here, T. So in def is def joined with out def, so is T joined with B, is the set of variables T and B, which is our in def for our complete basic block here. So if we assume that a variable x is live at the basic block exit of basic block n, then we have 4 possibilities with 4 distinct semantics here. So we have 4 cases, and these cases just give our combination with the information of a variable x is part of the gen set or and part of the kill set. So of course we have 4 options here. The first one, x is neither part of the gen nor part of the kill set. So we know liveness of x is actually unaffected in this block n because it just doesn't occur. If x is part of our gen set, but x is not part of our kill set, then we know liveness of x is generated in block n. On the other hand, if x is not part of the gen set, but x is part of the kill set, of course we know that liveness of x is killed in this block. And there's an interesting case. If x is part of the gen set and part of the kill set, then the liveness of x is unaffected in this block n, in spite of the fact that x is being modified in that block. So we see that variable x is live at the entry of our basic block n in cases 1, 2, and 4. But the reasons for this variable being live is different for each case. And our last case, case 4, captures the fact that the liveness of x is actually killed in n, but then we regenerate our variable in n. So we have something like a equals b plus c, so we're using it here, and then we're redefining c with 42, so that might be a case where our option number 4 might apply. So we can take a look at an example here. So we have a control flow graph for a simple program containing assignments, function calls, and a couple of if statements here. So we didn't explicitly notice the if statements here because, they're not relevant to our discussion here. And so we see we have 4 different variables here, a, b, c, d. And now we start to enumerate the definitions here. That's used for later analysis because it makes it easier to discuss what's going on. So, for example, our first assignment here in basic block 1 of b equals 4 just gets a label of b1, or our assignment here in basic block 3, c equals b plus c, is assigned a label c1. So we have a number of definitions, a1, b1, b2, and so on. So we enumerate all the definitions here in our program. And on the other hand, we are taking a closer look at all the expressions. So we have a times b here, for example, here. We have a plus b, we have a minus b, and so on. And a simple analysis is we can figure out that variable c in block 3 is read, so it's used here. And it's defined here on the left-hand side. So we have c equals b plus c. We're reading the old value of c. We're assigning a new value to c. So this value of c is contained both in the gen set of c, we're assigning something, and in the kill set of c, we're using it, and it's overwritten. Using our approach we've described before, we can do a trace of liveness analysis of all variables. And as you see in this table here, we start from our last basic block, B8, and we're tracing backwards through all the basic blocks, propagating the information. So, for example, in B8, we have a gen set of A, B, and C. So we're using A, B, and C here. And in B7, for example, we have A and B, or in B2, for example, we would have A and C. Accordingly, we have kill sets. For example, in B8, we are not assigning anything to variables here, so our kill set is the empty set here. Or in B2, we're assigning something to B, so our kill set of B2 is just our variable B here. Now we can actually try to determine our out and in sets, and we do this as we've seen before in separate iterations here. So we're determining the out and in sets as we've seen before for each of the 8 basic blocks in our program. And of course, we know due to our loops here, we can have changes. So our first iteration is not necessarily giving us the final result. So we need to find a fixed point here. So we go through our program control flow graph a second time, doing the analysis again, using the values we've obtained in the first step here. So we go through it again, and now we figure out the second iteration gives us the same results as the first iteration. So we know we've hit a fixed point, and if we have hit a fixed point, our analysis is stable. So we have convergence here. So this works out to be a quick analysis for this case here. So we know our data flow values computed in the second iteration are identical to the ones in the first iteration. We have convergence. We would get a different result if we had used the universal set to initialize it. So the universal set would be all variables just being used or defined in our complete program here. So this would be the set A, B, C, D. In this case, our variable D would have been live at the exit of B7 here. But if we take a closer look at our program, D is actually defined here and defined here, but it's not used anywhere in the program. So essentially, we could try to get rid of it with some optimizations. So for given variables x, now we can see how this liveness of this variable propagates throughout our control flow graph. So this propagation of liveness analysis discovers a set of so-called liveness passes. And each of these liveness passes is a sequence of basic blocks, so B1 to Bk. And this is a prefix of some potential execution path that starts at B1, so that our final block in this path, Bk, contains an upwards exposed use of our variable x, and x is either in our start set, or it contains an assignment to x, and we have to ensure no other block on the path contains an assignment to x, which would just kill and redefine its value. So we can look at our program again, and we noticed in color here some different liveness passes for our variable c in our example program. So we can start, for example, at this point here at basic block 4. So we're assigning a value to variable c here. Now this value gets propagated here. We're not doing anything with it in B7. We're propagating here to B8 where it's used, and then our program ends. So our green path might be one short option here. But of course we have different options for liveness passes of C. So for example, we also define C here in B3, C assign B plus C to our variable C. And now we branch to the right hand side on our pink path here. So we're not using C here, we're using it here. Okay, so we have B3, B5, B6, and then we're branching to the left, B7, and we're using it again here in B8. So this is another liveness path. And we can get yet another one by branching to the right instead of the left at b6. So we start here again, we go here to b5 and b6, and then we branch to the right. So we enter this loop here. So we get b3, b5, b6, and again b5, b6, and then we branch to the left, b7, b8. That is another Liveness path, and of course we can go through this loop multiple times, so we can extend this path here by arbitrary extensions of b5 and b6. And of course, a final path for C would be the one here on the left-hand side. So we're going from b1, where C is used, to b2, where C is used again, to b8, where C is used the third time. So b1, b2, b8 would be a third Liveness path for our variable. So what can we use Liveness analysis for? Of course, we want to enable so-called static analysis. So we want to figure out properties of our program at runtime, and these properties can be errors or possible errors in our program. These properties can be optimization opportunities. So one important thing in programs is finding uninitialized variables. So if there's a program path where we try to use the value of a variable, but we have never assigned a value to a variable before, the results of our program run can be unpredictable. So languages like C typically do not define the behavior of programs with uninitialized variables. So essentially, maybe we want to do something against this to avoid this sort of error. So if we have a program like this here on the right-hand side, we start somewhere, then we have an if condition, and inside of the if we assign x equals 1, and then later on we use our value of x in the second assignment a equals x. Then we know this definition x equals 1 reaches our use a equals x, but we have an if here, so we cannot be sure that x equals 1 is executed in all cases. So we might have runs through our program which just skip the if part here and then try to use the value of x without it being assigned first. So this is of course a common source of security problems, because we can't predict what value a will actually have afterwards in all cases. So we want to try to avoid this. Another case of the application of Liveness analysis is an optimization case. So we want to do so-called dead code elimination. So if we can figure out that a variable x is not live at the exit of an assignment of x, then we don't need to assign it at all, because this value gets overwritten in the very next instruction. So this would write values to memory, which costs time and effort, like energy. So we want to discover these useless store operations here. So at any operations that stores v to memory, so we write something like this one here to memory. If this variable is not live, then we can skip the store. It's useless because we're not going to use the value afterwards. So in our example here, we have a number of variables. So we have a global variable called global, we have a local variable called I, and of course you see we're assigning 1 to global, and in the very next step we're assigning 2 to global. We're not using the intermediate value of 1 we assign to global here at all, so our assignment global equals 1 is just not necessary. The same happens with the assignment here, because we're always executing a return before, so our third assignment is unreachable. So we can also leave this out, so we can skip this one, we can skip that one here. And the third case here is a bit more interesting, because we know our range of our variable I here, it's a local variable, ends at the end of function f. We are not assigning the value of I, which we've assigned 1 to, anywhere, and we know it's no longer available after we return from the function, so I is not used anywhere. So we can actually also skip the assignment, and we can also then skip actually the declaration of that variable here. So we can go from here by eliminating the stat store here, the dat store global equals 1 here, and this piece of unreachable code, and end up at an optimized function down here, which just sets global to 2, which is the only assignment that has any outcome after leaving the function and return from this function here. Another use case is register allocation, and we'll have a closer look at register allocation in an upcoming lecture. So if we know that a variable x is live at a given program point, we can assume that the current value of this variable is likely to be used along some execution paths, and so we can use this information for optimization. So we can say that variable x is a potential candidate for being allocated to a register, because we know storing it to memory doesn't make much sense right now, because we might need it right away in the next or the one of the upcoming instructions here. So keeping it in a register saves us quite some overhead, because we don't have to store it to memory and load it from memory soon after. On the other hand, we can also use this information if we know x is not live. Then we know if we have x allocated to a CPU register, we can actually reallocate that register to some other variable here without the need of storing the value of x in memory, because we know it's never being used anymore in the run of our program. So we're going to look at more details on register allocation later. Yes, and of course, if we can do live variables analysis, we can turn this around. We can also do dead variables analysis, just to sum it up. So we can just turn the definition on its head. So a variable is dead, so not live, if it's dead along all passes. So we can perform dead variables analysis here, and we would have to change the interpretation of our sets in n and out n. So if a variable is contained in n or out n, it is dead instead of being live. And of course, this is also already quite some old technique, so we're only looking at very basic techniques of data flow analysis here. So the first mentions of this were already in publications in 1975 and before. And there's some interesting reference here at reference 2, which is some information on security problems due to uninitialized variables. So if you're a bit interested in computer security, that might be interesting to look at. So that's all for now. Thanks for listening, and hope I'll see you in the next lecture. Thank you.